that is there. Any you start, you stop, your sensors, your level switches, your anything that is either a switch or a sensor, that's your input. Your output is anything that a switch turn on. Is a motor, a light, any thing that is actuated, then is an output. So if we look at this here now, what would our inputs be? To look at this that we have here.
Sorry?
Oh, on material A and material B.
All right, so we call the level switch A. And level switch B. Anything else?
Lower level switch and inlet
Lower
valves.
level switch. No, inlet valve is somewhere when the switch you turn on, so we would write that as an output.
Oh,
But
okay.
you're leaving two most important things. So let me tell you them now.
Start and stop.
Start and stop. All right, now your outputs. We're going to list the outputs as well. So what would our outputs be now?
The motor,
All right. Motor, which is the agitator.
all the valves.
The valves. So inlet, so inlet A, inlet B, and your outlet and the buzzer, because they specify that they want to, so we put in the buzzer. So those are our inputs and those are outputs. So we have to specify both sets of things whenever that's the first thing that we have to specify when we are writing our program. Now, let me just say, let me just explain what is very important, why we have to list the inputs and the outputs. Let me, you have to go bear with me with the technology because we have to, this is a show and tell. So let me just bring up some pictures of some programmable logic controllers and explain something very important. So all right. So let me just go to this here and discuss. Now, On the screen, you're seeing several different kinds of PLC. So PLCs can be very, very large, and they can be very, very small. Now, for example, this PLC that I'm putting up here in the diagram, this is an example of a small PLC. I'm not able to count the amount of inputs and outputs that there are. But according to what I'm seeing here, it looks like it have about 15 inputs and 14 outputs. All right, so you have PLCs like that. Then you have PLCs like the one that is here now, that you can add inputs and outputs. So all of these are what we'd call input and output cards. So you'd add and build onto them. So you can have several hundred input and output cards for your PLC. All right, so you can have small PLCs that you use. For example, the PLC that we show here is a small PLC. Right? It's a small PLC with very few inputs and very few outputs. This look like 1, 2, 3, 4 outputs, and I'm not sure how much inputs. 1, 2, says 8. All right. So what I'm getting at is that you use PLC to run your block making plant, which is a very small plant that you can operate in your backyard, and you use PLCs to operate the whole plant at Jamaica from Pittsburgh. You can stay from Pittsburgh and run your PLC. So PLCs come in all different shapes and sizes. So why am I saying that? So going back to our thing here now. I have listed my inputs and outputs. And I have here 1, 2, 3, 4, 5 inputs and 1, 2, 3, 4, 5 outputs. So the very Jamaican thing to do is, oh, we need a PLC. Boss, we need a PLC. I don't know much about PLCs, but I heard that you did it at UTech. So you know, we need to run this mixed plant. So how much, what size PLC are you going to buy? And then of course, we with our Jamaican selves, who love name brand, went to go for the $1 million PLC when we can get a $40,000 PLC that will cover the entire operation that is here. All right, the more inputs and outputs the PLC have, the bigger the cost. So if you know how much inputs and outputs you have, then you know what kind of PLC you're going to buy, or what kind of PLC you would need, how much inputs and outputs the PLC should have to function, to do the program that you want it to do. So you don't go and say you want the $1 million one or the $2 million one when you can get one for $10,000. And I know people say, but we would never do that. I was at UTech when UTech did it. UTech went and bought one PLC for $2 million. That was years ago, when $2 million would be about $20 million now. They bought a PLC for $2 million, one PLC for $2 million, when they had classes of 25 students that then they could have buy same PLC for 5,000. A set of PLC, not the same PLC to use that could have cost $5,000 at the time. So they buy the $2 million one because we're going for name brand. Because what happened now, they say, is the one that Jamalco use we want. So Jamalco use a Honeywell PLC, and the Honeywell tell them, say, if you want that one there, no, it's $2 million. And guess what happened after it was bought? Nobody never know if you use it. So it is there. And so it's a common engineering practice. I was just reading in the newspaper today that them spend, the auditor general department spend $5 million for a machine that nobody not using and knows how to use to print checks for pensioners. So No, they spend $2 million for the machine and $5 million for the software, and nobody don't know if use it, and they're still outsourcing all of the things that they need to do. So I'm not saying this willy-nilly. I'm saying that if you're going to be an engineer, then the first thing that you have to do is when you put in the inputs and the outputs, then you will know what size PLC that you would need for the particular project that you have on hand. All right, so first thing you have to do is put in your inputs and outputs. The next thing that we do is that we put in what is called addresses for the PLC. Now, the PLC that we use is Omron. And let me just explain why we use Omron and not, you have Allen Bradley PLCs that are common. The most common one up until recently in Jamaica was Allen Bradley. At Jamaica, they use Honeywell. And also at the Windalco, they use the Honeywell PLC. DNG uses Allen Bradley. Down the wharf, when we go down there, they use the Mitsubishi PLC and so forth. Different PLCs are used depending on your preference of brand and what it is that you want to do. Now, also important for me to explain why we at UTech chose the Omron PLC, because we were, first of all, at that time, they were the cheapest. They no longer are the cheapest. Them now competing with Allen Bradley in terms of costs. But at the time, they were the cheapest. That's number one. Cost is very important. Number two, they were the ones that would give the most support, meaning that if you had a question to ask and about a programming problem, then there was somebody in Jamaica trained that you could call and ask, and they would come and try to help you fix the problem. Allen Bradley and those rest didn't have anybody like that. The Mitsubishi one down the wharf is China control. That are the Chinese come in, do whatever they have to do, and then leave. And the Honeywell one, you have to go to them plant and spend another how much $1 million to get training. And they only train people who are working at places like Jamaica. They don't train, you can't just come off of the road and say, oh, I want to be trained to use the Honeywell PLC. Granted, as I will try to show at the end of the class, that it doesn't matter. Once you know to program one brand of PLC is the same thing for programming all. It's just slight differences in addressing. So we have to we're going to deal with the addressing. So now, when you're writing an address for an Omron program, is 0, we'll use 000 to specify as an input. And the next 00 is a physical location. So each of them has to have the three first zeros. You used to understand what I mean when we say the three first zeros are an indication to the processor that this thing is that we are there is an input, and the next two things are there to say, all right, we are this is where we are going to connect level switch A to. So let me just go to one of the things that we pull out. So this is a physical Omron PLC. There are some things that I just want to point out. This side is the input side, and this side is the output side. So these are the points. If you look at the points here, they are where we physically connect our switches and our wires. And if you look here, you see 0, 0, you see 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So what we are saying is that um, this switch 0, 0 actually. And then at this level, you have common, which we're going to come to later. And then 0, 1 is here. This is 0, 1, and this is common. We talk about common, which is basically 0 volts, but we're going to talk about that later. But you're going to physically connect your switch to this point here. All right. So the level switch is going to be physically connected to the input side. 0, 0, 0. And on your output side, again, you have the same thing, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So all of these are physical locations that we have. Now, when you come in to use the PLC, you're not going to be this little plastic thing that we have here that says out and in. Is you use the PLC one time, they disappear. They break off quite easily. So how you know the input side from the output side on the PLC is by looking at this up here. This PLC has, this input side has one command for the whole entire input. So the command or the power up for the input side is one connection. Connect powers up everything. The output side, if you look here, you see that you have several commands. So that is how you're going to know it, because you won't have the plastic to say in or out, so that you will know. This would have dropped off or been broken long ago. But you can always recognize by the amount of commands that you have. And also your power supply, plus or minus, that is here. You know that is the output side. So the output side is over here and the input side is over here. So input side, one command. Output side, more than one command. Yes, Mr. or Mrs. Michael.
Sir, so like when you're looking at it, since the ones that you take are broken off, is there some physical difference between the commands and the rest of them that we can use to identify? Could you like give a description?
So, like I said, this plastic thing that you see here, on all of them at UTech, it is not there. So what I'm saying is that if you look on this section of the PLC, this section here with the numbers,
Yes, sir.
the input side has one command.
Okay, sir.
If you look here, you see that there's only one command over this side. So that's the input side. The output side, if you look over here, when you look over the output side, you will see more than one command. You see several commands. All right. So you immediately recognize that the output side, because of the 1, 2, 3, 4, 5, 6, 7, 8 commands, while the input side is only one.
Yes, sir. I got that part, but like when it's not blurred out, is there something we can use to recognize command? Like is it shaped differently from the rest of them?
No.
Oh, okay.
The only thing you can use is this side have more command than this side, the output side have more command. And the other thing that you can use is this, the power supply. The power supply is on the power supply
Oh, okay, sir. Yes, sir.
is on the output side.
Okay, sir.
And that is always marked. All right, so back to our program. So what we would do after we have identified we would label our switches. So input is 0, 0, 0 and 0, 1. These numbers are arbitrary. All that is happening is that we are saying that when we are wiring, if we are wiring a start switch, it's level 3. And the same, similarly, we would do the same thing for our output. Now, our output is 0, 1, 0. That indicates that it's an output. And then we arbitrarily pick, assign where so each of these are assigned. So 0, 1, 0 indicates that's the output, and 0, 0 indicates the location where you are going to physically connect the thing. So you have your level switch, and all of those things as the input. So on your input side and your output side, the 0, 1, 0 indicates to the processor that is an output, or 0, 0, 0 indicates to the processor that is an input. And we will just making a distinction between the two of them. So or me to mix them. All right. Now, another reason why it is important for you to write down these things. So I just use two stories, true stories, for why we should document these kind of things. First thing, yeah, a couple years ago, cement company asked for new tech students, asked if we could get some new tech students. They were rewiring their PLC, so they wanted somebody to know who knew a little bit about PLC to come and help them to rewire them PLC. So we got a couple UTech students to that course. It was supposed to be a 3-week course. Sorry, it was supposed to be a 1-week course. Because they were running new wires to them PLC. Apart from the fact that they were them scared the daylights out of the, because when them turn up at the plant, them man them out the road, they say, so how come them people come get work and we not get work? Or, oh, we have a bond up listen or whatever. So they said they did quite perturbed because out the road man say, we can do the work. And how come we not get work too?
Sir.
Don't worry.
Sir.
I hear you.
A question. The 0, 1, 0, it is standard across all PLC?
No. So little later down with when you say across all PLC, across all run PLCs.
Okay, sir. Cheers.
If it's if it's Alan Bradley, then it is I mean input and O mean output, and so forth and so on. So if I let me see if we can find an Alan Bradley PLC program and to indicate. So I'm going to jump the gun. A little bit. To say that once we, let me see if we find it and then we can discuss it. A little later, I'm going to bring an Alan Bradley program, but what I'm saying is that it is standard for Omron, that brand. Each of them has their own unique way of addressing input and output. whether it be I or like I say or X. Some use X to represent the input and Y to represent the output and so forth. So that is one difference, but the run that is standard. Basically, the bigger PLCs don't use they use 100 instead of 010. And since while we are here, let me go back to the PLC again and just make another point. Where are we? All right, we'll go back to the diagram of the PLC and make another point. If hopefully you can see the point that time. Trying to make it as big as possible. All right, you see the number for the PLC? I don't know if it clear or if it blurred. It kind of blurred on my computer. So I don't know if you've seen the numbers.
I have the presentations already. I have all that I can find.
So you see the numbers?
Yes, sir.
All right. Now, if you notice that you have 7 and 7, 5 and 5. So 5 occurs 2 times, and 7 occurs 2 times on this PLC. This 5 is over here, and you have a 5 over here. So, on both the input and output side, if you look at the output side, you see that there's a 0, 1 here and a 0, 1 here. So what is going on? Right? You have 2, 5, 2, 7, 2, 6s, you have 7 and 7. Well, so let me just make that point here, is that what the PLC does is that you have 2 levels. So there's a cutoff. They kind of divide the PLC in 2. So the PLC kind of divided in 2. And you have this half over here and this half over here. So now 0, 0, 0 represents to the half over this side. And if you're referencing the input, then you're going to, the next level of input, you're going to use not 0, 0, 0, but 0, 0, 1. And same thing for the output is 0, 1, 0 for the half over this side. And for the half over this side, it's 0, 1, 1. All right. So for this particular PLC, some of them just have one level of thing. So it's just straight 0, 0, 0. But if you have 2 levels, is 0, 1, 0. The output would be 0, 1, 0 for one level and 0, 1, 1 for the next level. Now, if it is a PLC that has several what we call cards, so you have several more of them connected to each other, then each of them, the next one is going to be 0, 1, 2, and then 0, 1, 3, and so forth and so on. And the same thing for the input, 0, 0, 0, and then the next level is 0, 0, 1, and the next level is 0, 0, 2, and the next level is 0, 0, 3, and so forth and so on. So I was going to bring that up until later, but since the question was asked about the inputs. You understand what I'm saying, or it's not making any sense?
Sir, could you go over the part with the line in the middle?
All right, let me clear and just.
I understand somewhat, sir, but more.
All right, let me make this bigger again. So share it to go wrong direction. So, all right, if you're looking at the PLC diagram, if you look over here, this is the output side. look over here, it says 0, 0. But you see 2 0 zeros. You see a 0, 0 here. See a 0, 0 here. And then you see a 0, 0 here. So what I'm saying is that if you look at this, this is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 5, 6, 7. So there's a division here. So you go from 0 to 7 here, and then you start back over 0, 1, 2, 3, 4, 5, 6, 7 over this side here. This side here, you use 0, 1, 0 to address, to indicate that you're dealing with this side. If you're dealing with this side, then you would use 0, 1, 1. All right? So this address, this physical address here is 010.00, whereas this physical address here is 011.00. That is for the output side. Similarly, if you go up here, it's 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then here, it starts over. So anything over here would be 0, 0, 0, dot whatever the value is. So for example, this location here would be 0, 0, 0, dot 0, 0. While this location here, the same 0, 0 is 0, 0, 0, dot, sorry, 0, 0, 1. Dot 0, 0. So the physical, this PLC is basically divided in two. And I was saying that if it was, you added another card onto the PLC, then the next one, if you add another one over here, then it would be 0, 0, 2. If you had the same thing repeating itself on this side, and same thing for the output side. If you had another output level, then 0, 1, 2, and so forth and so on. And you have some PLCs that you have several levels of these things that just divide in two. And what I was saying is that the smallest PLC only has one level. So we're dealing with the PLC as if it is the smallest one in the program right here now. So we're just dealing with one half of the PLC. Any clear, or are you still not understanding what I'm saying?
Noted, sir. Yes, sir.
Clear or no?
So basically, this is PLC 1 and PLC 2. Well, I'm never technically correct. PLC card 1. PLC card.
See it now.
Sir, like how you have two different PLC, right? The two of them can do like two different things simultaneously.
If they can do two different things simultaneously, yes, the program is going to make it. So you mean if you can use it and run your mixing plant with your two inputs here, and then over here you have your conveyor belt, and it is running the conveyor belt and everything like that.
Yeah, like that.
Yeah. But it's not because it's two of them. It's just how you write the program. No, lie. Yeah, you can write it. Yeah, so you write the program that will determine. So you can use one side to do one thing and one side to do the next thing in your plan. And turn off and turn on whichever side you. But you have to be careful how you write the program. Because it is just, if you decided that you are going to take the PLC and wire the thing so that you run one wire from over here, so, or run the next wire from over here, so. You can also do that. It's just how you write the program. The program is just your slave, you know, do anything what you tell it to do, and whoever you tell to do it, it will do it. So you can technically run two different things with the two different sides, or you can use the two sides to run one thing. Suppose a bad mind and you somebody else want to use the other side to do something. I said no, because we use wire up on both sides and everything like that, and we have one program. The only thing though is that all of the things that you are going to do, you can't have two different programs. It has to be two different blocks within the program. Two different subprograms. So subprogram one run one side and subprogram two run the other side. But you couldn't have two different programs. The PLC has one processor, so it's only going to process the thing. Process one program at a time. You can only download one program at a time to it. All right? All right, so we could go back to, we digress wholly from, so we are here. We said that we would list our inputs and our outputs. Oh, and I was saying, given the thing about the plant, when they went to the plant and went inside and what, so they want the PLCs was in one room, panel room, and everything that was connected to them was all over the place, different parts of the plant. And they didn't know, so there was no documentation to say that level switch A is connected to 000.00. So they had to be tracing the wires back to the panel. So take the wire from level switch A and go back to the panel, follow it through and see which part it is connected to, which is a very bad practice, but that is the practice that is done all over Jamaica. The second thing was that I went to a plant, the water commission plant down Bogue, and they were saying to me, oh, well, some man from France come here, and anytime anything go wrong, you know, we have a problem, you know. So I said, then if never leave a manual where you put all of the things. They say yes, but it's written in French. So them know every time that any little thing, the man have to take in British Airways from France to England and then from England to Jamaica, spend 25 minutes fixing whatever problem, and spend the rest of the week on the North Coast drinking Red Stripe until he go back to France and wait until they call him again. Now, that is a waste of money. Should have a basic understanding and have the basic knowledge of and everything so that you can run the thing more efficiently. All right, so that is that. You list the input, you list the output, you give each input and each output an address. All right, now the next thing that you have to do is write what is called a statement list. Algorithm. Now, I have discovered that Black people don't like statement lists or algorithm. Black people like to write programs straight off of the bat. But it is good practice to write the statement list so that you can dry run the program, because you don't want, it's not one C++ program where you're learning how to solve a quadratic equation. And then when you write the program to solve a quadratic equation, it don't work, so you go correct whatever, what corrected it. This is a program where when you download it and press run, something is going to start spinning or something going to turn on, current will start flowing, And if you mess it up, you can lose the job or an arm. So you have to test the algorithm to make sure that it is working properly. All right, so what does the statement? Basically, I just like to say, we say, what is the first thing? What is it started? When does it start? I put an asterisk to say what is started and say when it ends. And we go through and do that. So, all right, so for our program, this mixing tank, when would physically, when would the process start? You walk into the plant, what are you going to do?
Hit the start switch.
And the
All
start
right.
button.
So it starts when the
Yes.
start button is push. And what is started when that happens? When you push the start button, what do you expect to happen?
The
Some kind
motor
of end
supposed to
effects
turn
are turn
on.
on.
Huh?
The motor is supposed to start to
That's
indicate
not the
say,
first thing. Well, look at what's supposed to happen here. Run back through the process in your mind. When you press the
The
start,
inlet valve.
all right, so inlet A supposed to activate to let in the water. And
The inlet valves are supposed to reach level material A.
so ends when I'm going to put LS A is triggered. Now it is 1R, I don't know, whatever. So the second thing now is that the second thing starts when the first one ends. So LSA is triggered. So what is started now? When the thing reach up to here,
Inlet B, sir.
inlet B. Now when does it end?
When LSB is triggered.
It ends when level switch B. See here, you're in trouble now. So starts when LSB is triggered. And what happens there now?
The
When you
motor turns on
so the motor turns on. And when does that end?
after 25 seconds.
All right. So after 25 seconds, what is triggered then?
Is it the outlet?
The outlet. And when does that end? Work up to the specification.
Lower level switch.
Yeah, so it ends when the
When the
lower
lower level switch is triggered.
when the lower level switch is triggered. All right, so this is our thing sequence in order. So the next step after that now for us is to write the program. All right, so before we write the program, we just want to look at some programming constructs. Now the program uses what is called ladder logic. And ladder logic is an iconic language. Whenever most of the time when I don't know if you ever see them use Lego robotics or one of those things. Those are iconic languages that they use to program these things. They use the same PLC type program model to program. So let me draw a line and put some programming constructs again over here. All right, so I'm going to put over here. Now, the two basic things that we use in ladder logic. This is a normally open switch. So this symbol here with the two lines represents a normally open switch. And we have another symbol here. This is a normally closed. I don't know where my mouse gone. And the other one that we use is actuator, motor, whatever the output is. So this represents an output. And this is normally open. Now, what do we mean by normally open? Normally open means that when you press the switch, it turn on. So it's normally off. Normally open means not can say normally off. And this one here is normally closed, which means it's normally on. And when you trigger it, it turns off.
All right.
Okay. So you trigger the switch, it turn off.
Hold on. Sir, normally open. Just to clarify, when the switch is in the it's in its normal state where it's not energized, it is in an open state, correct?
Right.
And so when you energize it now, it closes.
Yeah.
And then normally closed node is that when that switch is not energized, it is shut. And then when you energize it, it's open.
Right.
All right, that's all I'm not.
All right. So let me just you have to bear with me with the I have to find the pictures. Going on should have had a going to UTech this week to go take up the PLC and everything, all the other things that we need. Let me just give me a second here. Finding it. Let me just see if I can find a diagram. Not finding what I want to find. I will show you next week what I want to make clear. All right, now can't find it. All right, so here is a thing that, well, I need to point out. Maybe I might confuse a little bit. This switches, when you buy a push button switch, especially a push button switch, you can either wire normally open or normally closed, right? So it comes with a wiring diagram. Most of them come with the wire, unless it's the simplest one, and they tell you where we come normally open or normally closed. So you can buy a switch that is normally open. You can buy a switch that is normally closed. And
so one example of the normally open switch are like the they call it again the moment switch.
Yeah. All right. So now, just a point. When you start programming, then you understand more what I'm saying now. The program, all PLC programs assume that all switches are normally open. That you wire them into the circuit normally open. So we're going to be writing a program, and some of the switches are going to be we're going to use the normally closed designation in the program. But when you come to wiring up the circuit, all the switches that you have in the program are to be wired normally open. It don't have nothing to do with the program. So when you come to wire, and if you are to connect the wire to the switches, like I say, you can connect the switch so that it can be normally open or normally closed. When you are wiring up a switch to for a PLC program, all switches are to be normally open. All physical switches are to be normally open. It don't have nothing to do with the program. The program is going to operate based on its own thing, and it's going to assume that all the switches are normally open. Like I said, you will understand more what I'm talking about when you actually come to wire up. But I'm just putting that out there from now. All right. So now, so these are some of the constructs that we are going to use. These three. Now, the ladder logic goes like this. You have a 24 volt, you have a switch, let's just say that's normally open, and you connect it to so now, what over this side here is 0 volts. So now, what is going to happen is that what you're saying is that if I connect switch 000 on my PLC and I connect the motor to 000, what this instructs is that the current cannot reach the motor until I close this switch. So when I close switch 000, then it turns on the motor or whatever the thing is connected to 00. So now we have some designations that we use. So first thing is AND. So if I have this program, this in my program. So let's say that I have 000.00, and this is 010.05. This means that both of these have to close before this can turn on. All right. So this is AND. So both this switch at 00 and 01 has to close before whatever, let's say, is a motor at 05 turns on. Similarly, we have OR connection. My OR connection. So in this way now, if I close this, then current can flow and reach 02. Or if I close this, then current can flow through here. So this one here is either of the two switches can turn on whatever I've connected my output side 02. All right.
And
So
this could be applied, sir, at if you put either switch at say two different ends of a room or a tier or something like so.
yeah, it could apply in that particular situation. So you can use any one of them to turn it on.
Or even as a emergency lock off.
Emergency lock off. All right. So now let me just deal with the most important construct now. Is latch. Yeah, let me deal with this first. So now, if when I have this in my program, what it says is that if I connect this, then current can reach 02. If I trigger 03, if I push 03, then what is going to happen is normally closed, so it's going to open when I trigger it. So when it opens, then current can reach 03, 02, the motor. So one of them closes the switch and the other one opens. So this is a kind of start-stop mechanism. The problem with this is that you have to have a single throw switch, meaning that the ones in our houses that when it goes from one position to the next position, it stays there. Because if I push button switch, then if I want this motor to continue running and have a push button switch, then I have to keep my finger on the push button. Because the minute I take it off the push button, then we go back to square one and the thing is going to be off. So how do we overcome that then situation? When we have if we have this line in our program, I want to turn on the motor, but I want the motor to stay on. Well, that is where now we have the latch. You probably would have heard about a latch in digital electronics. A similar concept. So here's how this works. So let us say that this is 000.00, and then this is 000.03. What I have down here is going to be 010.02. Now, the output acts as an input. Now, physically that can happen, but is code we're dealing with, is a program we're dealing with, in a processor. All the processor is doing is memorizing when this what turn on and what turn off. And storing that whatever happens physically in one of its memory locations. So all PLC programs allow you to use an output as an input. So in other words, if you turn on the lamp and the lamp turn on, you can use the fact that the lamp turn on to turn on something else, turn on a motor somewhere else. All right, because like I said, the processor allows you to use an output as an input. If we were to use an input as an output, that is a different story. We have to go do a little bit of programming, a little bit of constructing to do it. But as it is right now, like we said, you can use an output as a switch to turn on something. Now, these two have the same address. So let us see what happens now. I close the switch. I push the switch. Current reach 02. So 02 turns on. So therefore, it's going to close because if 02 turns on, then this is going to close. I take my finger off the push button. So this opens back. But current can still flow through this part here. And the only way that I get it to stop is if I press this and open it. Now when I press this and open it, and I open this switch, then current cannot flow anymore. So this turns off. So this turns off. And when the two of them turn off, then what is going to happen is that you're going to have 0. Everything is going to turn off. The only way it's going to turn on back is if I push back the switch here and close back the switch here. So the latch when we have the program like this, then this is called a latch, and this is the programming construct that we use. Now, whenever we're writing a start stop, yes, if you have a single throw, single pole switch, then you can write the program like this. But here's the problem that you have. So 2 years down the line, switch stop work, or somebody decides, well, we need to change out the switch, and then buy a push button switch. So you have this you have the program like this for the start and the stop. This only works with a single throw, single pole switch. This construct works no matter what. So this is more universal when you're writing your program. And it is important when you're writing a program that you bear that in mind. So you want to take into consideration. So if I change the switch, if I change the output, if I change the actuator, if I change this, is the program going to be affected? So if the program, we have to write in the most general terms. So,
Sir, why is this configuration important to be used? Because how I'm looking at it, the motive is to run and keep running. We just put in one switch and make it run. When it's ready to stop, we just turn it off. So why is this configuration important?
This configuration is important because we're going to be using it up here. And if you automate a process, if you are going to turn on and off this, you physically turn on the switch and physically stand up there and wait for however long and then turn it back off, then fine, it's not a problem. But if you expect the thing to run automatically, then no, you're going to have a problem. All right. So you're going to need if the process, remember now, right? This thing here, move on it, not going back. All right. Yeah. So the algorithm that we have here, we're going to be implementing it, and it's going to have to go from one to the next, to the next, to the next, to the next, without interference from mankind. After you write the program, you go from step one to step two to step three to step four without any interference. So if you are using this construct here, this one here, this particular construct that we have here, this, all I'm saying is that it depends on the fact that if you have a manual switch that is once you turn it on, it's still on, then it's going to mess up a program because you would have to turn it on and turn it off for the program to run. As you will see what I'm talking about.
Okay.
All right. All right. So now,
Yeah.
I'm trying to get this thing to go back to where it was, but it not pay me no mind. Let me rewrite this.
Undo now, Erickson.
Huh?
Undo is
That's
not
what
working.
we press it about 40 times.
When they erase everything in us.
Well, I waited for it to do, just come and just go bloop and erase everything because I keep on pressing it and nothing happen.
So you
All
don't
right.
know if no simulation suits where you can practice plans on the gun.
You mean these?
Yes, sir.
You know, the simulation suit, only is with simulation suit, you know. It's only we practicing for.
Okay. What's the name of it, sir?
This?
That's a simulation suit?
You mean
No,
for what? For your talk?
It's a practice lot of
You mean
logic, sir.
to practice what? The
The
programming?
Yes, sir.
Oh, then that's why we tell you to download CX Programmer.
CX programmer.
CX1.
Okay. I never hear that, but I'll go feed now.
CX1. It has a programmer, simulator, and designer.
Oh, it's for the Omron brand.
Yeah.
All right.
Because that's the PLC that we have at UTech. So
It's CX1 or CX program?
CX101E. Yeah. I'm gonna say like automation suit software.
CX1 and CX program are different, sir?
CX1 have the three of them, you know, three of them.
All right, sir. Thank you. Can I continue?
Yeah. So CX1 have the programmer, simulator, and designer. CX programmer is just the program itself.
Okay.
All right. So let's use this thing here now, and we're going to write the program. So So we have a thing that says starts when push button is pushed, start button is pushed. So I'm going to write the program over here. So first line in the program, we said start. So this first button here is when it starts. This is what stops it. We say what is started and we latch it. So each line in the program, that's what we're going to do. So starts when the start button is pushed, and we know the start button has address 000.03. This is my start. Stops when level switch A is triggered. So level switch A, the thing for it is 0.00. What is started is inlet A, and inlet A has address 0.10.01, and then we so that's the first line of a program. Let me draw a line here. The second line of a program says starts when, so this is LS A. So it starts when, say what stop it, what is started, and we latch it again. So LSA is 0.00, and then what stops it is LSB. Our address for LSB is 0.0001. And what is triggered is inlet B, 0.10. I'm going to leave out something that we put in at the end. Level switch inlet B is 0.10.02. And we'll latch it. So what I'm getting at now is that it's very easy to write the program for the most part. So now the next, so this is LSA. LSB, inlet A, inlet B, so the next line is LSB, and so here's the part that I need you to pay attention to now. So starts when LSB is triggered and ends when 25 seconds. So this is our motor and the address of the motor. 0.10.00. Now, the step 3, we start the motor and we're going to stop the motor after 25 seconds. Now, one of the things that the program allows you to do is put in some timers. So I'm going to call this T1. This is our timer, 25-second timer. And when we're writing timers in the program, we write it as T1 or T2, T3. It starts as 0, but I don't like using 0. So you write timer 1. So we have a timer in the program, and it's going to turn off after 25 seconds. So here we have 0, 1, 0, that's 0, 0. And then the fourth line is that when the timer finish timing, so what the timer does is that it's going, when we configure it, it's going to say 25 seconds. And when it's 25 seconds, it's going to set a bit high in the processor. And that high bit is what, when that goes high, it's going to turn off this and turn on down here. So wherever it is in the program, when it goes high, if you have it as normally closed, then it's going to open in the program. And if it's normally closed, normally open, then it's going to close in the program as when the bit goes high. And then what turns it off is LLS, which we have as we never put in LLS inside of it. Oh yeah, 00002. The outlet was 010.03. There's one thing that we never took into account here is, let me go back to the program. When the mixing process is complete, a buzzer will be activated and it will remain on after 5 seconds and it will automatically be turned off. So we left that out of our, so there's two things that we need to turn on in the program at the end. So let's just discuss how we put that in now. So we'd also need to turn on the buzzer.
So you need to put in a next timer.
So we need to put in a next timer. Turn it off. So we're going to call that T2, 5 second timer. Now, so that would be our program, right? But there are some things that we need to put in with the program. We need to configure both our timer 1 and our timer 2. So now, when we're configuring it, as you will see when we write in the program, we're putting TIM1. Now, so the timer 1 is for 25 seconds. So for us to put in 25 seconds, we have to put in number sign so that we indicate to the processor that is a decimal number. If we don't put in the number sign, then it is going to think that it is going to treat the number as a hexadecimal number. So we have to tell it that it is a decimal number, and you tell it is a decimal number by putting in number sign. Now the next thing is that the timer counts in default time of 0.1 seconds. So if it wants 25 seconds, then it has to count 250. You have to add an extra 0 to say that, because it counts 0.1, 0.2, 0.3, 0.4, and so forth. It doesn't count 1, 2, 3, 4, 5 when it's timing. When it's counting, that's a different thing, which we'll talk about next week. So what we have to put is 250. They add an extra 0 to whatever time it is, because you add it is 1/10 of a second you're using, and not full second. Now, when do I turn on this timer? Well, all you have to do is look, is timer 1 as LSB that you use to turn it on. When we finish, I'm going to address that. LSB address, we didn't put it down. 00001. So under normal circumstances, whatever is connected to the timer that turn on the motor, then we use it to turn on the timer. So I'm going to do that because that is the standard thing. But we have a little discussion that we need to make at the end. The next thing that we have to put in is the timer 2. So we put in TIM2, number sign, it's 5 seconds, so we put in 50. Number to indicate that it is a decimal, and 50 because it's 5 seconds we're counting. So it's 50.1 seconds that we're counting. And what turns on, what is to turn on timer 2 is timer 1. So we look at the beginning of the rung and say timer 1. And then, so those are the 2 timers. And then finally, at the end of the program, we're putting in end. Now, the PLC that we use doesn't need an end. But if there's no guarantee that you're going to be using Omron or that brand of Omron. So that is why we're putting in the end. The program itself doesn't need an end, but even other versions of Omron programs, you have to put in an end or the program will work. And there are other PLC programming things that you need an end or else the program won't work. This one doesn't need an end, but for good programming practice, we're putting in the end just the same. Now, so this would be our program. So we would simulate it and run it and see if it runs to specification. And then we would test it on the real thing. Now, we tested this kind of thing physically. And when we tested it and run it, there was a problem. So we had to go back to the program. And so this is part of the thing that you have to, you can write the program and test run it in your desktop, run it, go through the algorithm, see if it works. And then you simulate it, see if it works. And everything is fine. And when you do the physical thing, it doesn't work. And here where the problem was now. This part of the program, the timer, remember we said that it is LSB that we're using to start the timer?
Yes, sir.
Level switch. Now the level switch is a switch. Let me draw like a diagram to try to explain. Wait, where? Oh. So this is my tank. This is my mixer. My level switch is a switch that, just like this switch in your toilet tank. When the thing starts to spin, the water level doesn't remain constant. It starts to agitate. So what happens is that your level switch starts to go up and down as the water starts to agitate. So what that does, it kept on turning on and off and on and off and on and off the timer. So it messed up the whole entire program. Right? So it couldn't time anything, because it kept on just vacillating. So it messed up the program. So we had to go back to the program and change. All right. So I was making that point to say that you can sit down and work your way through the program and see everything is fine and everything works, and you do the simulations and everything fine and everything works. And then when time comes for the practical thing, there's something that you could never have accounted for. So we don't use the level switch B. Let me tell you what we changed that. Since it was giving the problem. Huh?
That's what I was gonna say. Change that switch.
Right. So we didn't use that. We didn't change it in the change the switch physically. We just changed what we use in the surface. Level switch B started the motor, so we just use the motor as a turn on. Now when the motor turn on, it stay on. So level switch B started this, so we just use this as our turn on for the timer. And once the motor turn on, because it's latch, it stay on. So we didn't have the problem anymore.
So once the motor turns on, once the 25 seconds elapse, it stops.
It stops.
Okay.
So this was our program. This is our program. All right, so now, so what I'm going to do, let me just take a picture of this so we can go to the simulation. So I'm going to have it here for reference. Okay, I read this though. All right. So after that, we are going to go and write the program. So we'll go to our, CX programmer to write the program. All right, so we go bring up CX program.
Which version of this is of software you're using?
Huh?
Which version of the software you're using?
This one is the CX9.
Okay.
But it don't really matter much, you know. There's not, if you're using up to CX4, I think CX4, there is not much of a difference. All right, so we'd press on the file and open. And then the thing that we have to change in this is this. We have to find the one that we are going to be using. Now, the one that we have in the lab is CP1H. The default that comes up is CJ1M. And we used to have CPM1A and CPM1. CPM1A is the smallest PLC you can buy. CPM1. So you put in the version that you have. That is very important because if you don't put in the correct version, then what is going to happen is that it's going to create problems for you when you're running the program, because the addresses are slightly different for input and output. Okay, so you're at the programming interface. So what you do is you have your switches here. You have your normally open switch, you normally close, and then you have your output.
How you reach this? My thing blank, you know.
You click on the new, like you see them like when you Microsoft Word.
Oh, okay.
And then you put in CP1H, and it's supposed to carry it to here. All right, So just a few things now. So you click on the what you want. So the first thing you want is a home switch, and then you put it in the blue spot. And then you type in the address. Yeah, what's the first address that we have here? 000.03. Click OK, and you say what it is. And it is the start switch. Press OK. Now, a little point here. You see this red line? It is very important while you're writing the program to pay attention to this little red line. When the line is properly done, then the red line will disappear. But as long as the red line is there, it means that there's a problem. All right, so we need a normally close switch. You click on the normally close switch, bring it down to our little blue spot here. And what I have here is that it is 000.00. Okay, and then it is level switch A. And then tab is that it's an output, so I click on the output, carry it down. And the address is 010.01. And it is
01 or 01.
010.01.
All right, I did that deliberately. Let's just make the point here. Inlet A. All right. It will put in the 01. All right. So now we have to latch it. So we're going to go and click on a little line and then connect it here. Sorry, connect it here. Little bit outside of the box. And then, oops. 010. 01. So that is our first line, and you see that the red line disappears. And so we go to the next line. Now, persons have a tendency, when you finish your line, you have to go into the next box and the next line. So we'll click it 010. All right, so we're not going to type out the whole entire thing. Yeah.
Sir, that second line, inlet A. You see how you want to go to underneath the start? I want to go underneath LSA. How we change that?
All right, so let me check it. Let me. All right. So you put in 000. And then you say you put in the line and it is coming over here. Yeah. So you're putting this first as suspect. and then you put in this line and it coming over here. You have to put it nearer to the side that you want it to. So what you have to do is now, if you put it over here, then you have to go and click and delete. Press delete, edit, cut, or edit, or delete again. Delete to remove it.
Okay.
So now this line is supposed to sort out itself. All right, now it don't sort out itself, which means it have a problem, so I have to remove. And I see that the red line disappear. All right, so I have to remove this.
Got it now, sir.
All right. The 1002 is inlet B. And then, all right. And like I said, I'm going to do everything. I just want to illustrate the point 0, 1, 0, 0, 2. All right, I want to go to the timer. So that's the third next line. So let me just put in that line and then put in the timer. So that's 0, 0, 0, 0, 1. Now, when you put in the timer, you press T1. And whatever you want to call it, timer 1. And it's connected to 0, 1, 0, 0, 0. Motor. Every time you want to get rid of one of these implements here, you go back to the little white arrow. All right, so now I want to put in the, well, might as well just go through. This is T1. Switch 0, 0, 0, 0, 2. This lower level switch. Um, 01003. This is outlet. And then connecting it to T2. And connecting it to the buzzer. Buzzer address was 04. Oops. This is not going to be a problem. Change the timer to.
Sir. Okay.
All right, so now the timer. The part where I put in the timers. So first we put in the switch to 01000. And then no. All right. So I hope you never drop asleep because I need you to pay attention here now. The timer is a function. So you have to go here until you see new PLC instruction. You click on that. Because the new PLC instruction is what we used to call function. Now I'm going to click on details so we can just see. Now, function is where you can fill in all because you have many different functions. See, if I type in A, you see that it talk about acceleration control. I was seeing if they had or then change it add to plus. Plus there. So you have many different functions. So we want the timer. See it have 10. So now we want timer. So we press TIM. Then we go to the blue section that is here. Click on that. And it's timer number 1 we want. Now what is not obvious is that we need to put in the time. We have to click below that. There are other ways of doing it, but I will put in number and the 250. I press OK. And then we see that the timer goes in. So let's just do that for the second timer. It's T1. Again, we go into the instructions. And like I said, it's just like a calculator, but with wholly more functions. So, so this is another timer. Number 2, and we click underneath it. This one of the quirks of the program is not obvious. Number sign and 50. Like I said, there are other ways to do it, but we're just sticking to the tradition. And then now for the end, we have to type in end for the program. We go back here again, go here, and type in EN, and we say end come up, and press OK. So that would be our PLC program. Now, so we have our PLC program. So now what we normally would do, if we have the simulator, because before we go and wire up to the plant and connect and do this and do all those type of things, we have to make sure that the program is running. I mean, we might do a little check and see if it runs, if we have everything okay. But we'll go and simulate it first. So we'll click, we'll go PLC, and we'll go online. So we'll say, go click PLC, and we'll say we want to go online. And whenever this occurs, that is a problem that will take years to fix. So, because that means that something is wrong somewhere. I'll check over here first, see if you have the right CP1H, and then I know what is the problem. So here's what the problem is. I have to go back and fix all of them. Oh, shoot. All right. CP1H. So I made an error when I was talking to you. I was still thinking of CP1A. So I'm going to have to add a 0 to all of these addresses. 100, not
So is a fault caused by the type of PLC you chose?
Yeah. Whenever you see that, there's always a problem with the type of PLC you chose. And then since the PLC that I chose was correct, then I look back at the addressing and I realize that that is where the problem is.
Okay, so this second one just now output card uses the 100
the CP
identifier.
Yeah, CP1H. All the time I've been talking to you is CP1M I was having in my mind.
Okay.
So let me go through.
So sorry, you can give like a worded overview again of how things supposed to flow, and let me cut out for a while, if that's okay.
Meaning how?
Yeah, like I see I have the inlet here, so wire parallel to the start. Why is it like that? You know, and stuff like that.
Let me fix this.
All right.
But whenever I tell you selected port does not exist, there's a problem with the addressing or with the PLC that all right. So we go again. Because here's my problem now. Probably have to go type over the whole entire. Oh, these over here. Sometimes you end up having to type over the whole entire program. I think it's a fault of their program, by the way, because one says 1010 and then the other one says 100 and still a mistake where no. Error, error, 1, timer 1, timer 2, T2. All right, so see, that works. All right, so I'm going to come and bring it back in. Okay, bother. Type this back over. Yeah, we'll just see if I can find what is it. Ah. Okay. All right. Here what? You just leave it out because, like I said, I'm not typing over everything. It's telling me something that I can't bother with right here now. I mean, I have to type over back everything. All right. So here what? Next week, I'm going to go to UTech, carry the PLC itself, and so we can have a proper run through with it. All right, so we stop here for today. Like I said, I'll try to sort out the program so that next week we can both simulate and run it.
Okay, sorry.
Because it refusing to change for me.
Okay. So remember to drop the video, the recording links in the group, sir.
All right.
Sir, did you say that we for this is face-to-face labs?
Well, you need to know to wire up the PLC. So it's 10 persons I see here. So the only
Probably have some more tomorrow as well, sir. Remember.
yeah, no, say if it was 10 persons, then I would just say collect the PLC and collect the thing so that when we're talking, you can just wire up the PLC at your house.
Yeah.
But if it's more,
We can't come link it tomorrow and give one to Kevin, sir.
yeah, that's
Yes,
what
sir.
I
That
said.
sounds beautiful, sir.
No, you can't do it because we have to work out too much people. So
All right,
can't do it yet.
All right.
All right.
They have some other PLC that, but they're hard to use. They some other different type of PLC. Oh, one last thing before we leave. I had wanted to, but when I see it, so this is the program that we're talking about. But I just wanted to show you one last thing. So let me just bring it up on the screen. So just give me a second. All right, so we have the mixing tank. This same diagram, but what I want to show you is the program. Basically, leave out the third part about the cyclone. The cyclone is just have to be there for everybody. The start and the stop. But if you look at the program, you see that it's basically the same as the program that we have. Yeah, this thing is going too fast through the thing. You have to have a timer. It's just that how you configure the timer is different. But the ladder logic is the same, basically. And how you address the timers and the inputs and the outputs. All right, the dollar sign, the percentage sign, and so forth. So 10.2, and the next one, the zero output is zero, dollar sign Q, and the output is zero, and the input is one, or I. But the point that I wanted to make is that once you understand the PLC programming, then to transfer to another programming language, another programming language, programming another type of PLC, is the addressing that will change and how you address the inputs and output. The basic ladder logic that they have for it will not change. All right. So if you go through the basic ladder logic circuit, it's the same thing with the buzzer and turn it on and so forth. There might be a few little differences, but not anything major that you wouldn't be able to understand. But the program basically is the same no matter what it is that you're using it and all right. And one other thing too that I just need to mention, I was fortunate enough to get a trip to China. A student from UTech was doing a master's, get scholarship to do a master's there, and they wanted to invite somebody to come teach, and then asked me to come and teach. And I was trying to tell him, say, me not going because me don't even jump. I don't want to be airborne that long, so me don't know how me will reach China. And go on the plane, so let me spit and reach. But the thing that I discovered was that part of the things that Chinese want to understand, they use PLCs extensively in all the industries, but the English is beating them. The English is beating them.
I see.
So,
No, continue.
So therefore, part of the thing is that if you see that they whatever the thing that they're programming is not in Chinese. So we have a distinct advantage. All right. And they wanted people to come across there who speak English so that they can interpret all of these things for them. So they're not that far ahead of us as well. We love to think, say, boy, them advanced and them. No. Same thing them are learning for them classes, same thing we are learning in our class. As a matter of fact, some of the things where we are learning, them never hear about. Some simple little things. And so would like us to take advantage of that kind of situation of our understanding of this thing, and we understand English, so therefore there's no difference in how we should see ourselves as opposed to other nations that we think supposed to be well advanced. They're only well advanced because them are, when we say well advanced, so they're all because them take some risks that we're not willing to take. All right. With their money, with their industries and so forth, they take some risks where we're not willing to take.
Okay, sir, continue.
Yes. All right. So next week I'll fix this, and then next week we continue from there. We're going to talk about looping and all those type of things within the program. Suppose we want the program to run continuously and all of that. And I'm going to check and find out how much PLCs we have so that we can decide what we're going to do. All right.
Okay, remember to upload the video, sir.
Yeah.
Sir, quick question. Can you change the time you have on the timetable? I would like to do mechatronics in the system, but there's a clash. So I'm wondering if based on your changes, I think the practical
we're supposed to be running this class tomorrow.
On Friday, yeah.
We're not running the practical on Friday. This is the class we're running on Friday. Same thing that we have today. We're running it tomorrow.
Okay.
But Tuesday, when we have a practical, we're not going to have a class, a physical class, but we're going to give you exercises to do. And you do them during that time.
Okay. Well, there's a clash with industrial
What?
instrument and control system.
When? Tuesday?
Yeah, there's a class on Tuesday from 3 to 5. As
Mm.
Tuesday the lecture, and Monday is a practical from 2 to 5. I do modern controls as well. But the thing is that I already did the modern controls on computer base.
Mhm.
So the thing I was wondering if you can make the adjustments so I can be able to add it.
To modern control?
Yeah, modern controls so I can do mechatronics as
So
well as
what change you want to make the modern control?
all right. I can send you an email and then with the explanation and so
Yeah, all right.
all right. And then if anything I can show to you and
Mm. Mm-hmm. All right.
let you know. 'Cause I know the system for algebra is still down.
Mm-hmm. Okay.
Mr. Fraser,
Mm-hmm.
I messaged you on WhatsApp. I was the one asking if you could increase the class size for
Modern control. It's not
yes
you one.
sir.
It's not you one. So when I go up there tomorrow, I'm going to talk to them and tell them to increase it.
Okay, sir. Thank you very much.
Sir,
Mm-hmm. I hear you.
sir.
Yes, I hear you.
Yeah, I was asking if you were still trying to get the other occurrence on the
Oh,
system.
I didn't I didn't send it in. I didn't send the thing to I send the email tomorrow. But make sure you send a WhatsApp message tomorrow. So
Yes, sir, I will.
all right. So tomorrow I will send the email. All right.
All right, sir.
All right. Cool.